Thank you. I'm Anat, and I will tell you a little bit about one of our solutions, which we use an algorithm oriented for the casino, for gambling, in order to improve hardware validation process inside Intel. So let's start with a little bit about my group, Advanced Analytics. We are about 150 people, everyone in Israel, and we solve strategic problems to Intel in areas of machine learning and big data. So let's start with the problem. To understand our problem, I will describe a day in the life of Omer. This is Omer. He is a hardware developer in Intel, and he comes to work like every day, prepare himself coffee, and then start to write a code. Hardware development in the first stages is very similar to software. You need to write RTL code, which will later be part of the chip. But in the first stages, it's like every other code. So now, today, you need to write a new feature in the area of power management. So he starts working very quickly, and he finished the feature, and now he needs to check his code. So you have testing like any other process for development, but hardware testing is a bit different than software. In software, developers can write unit tests that check each functionality of the code. But in hardware, the code is too complex. They can't write unit tests. They can't write tests for each functionality, and they need to use general purpose tests. These tests are there is a pool of tests, of general purpose tests. Each test can run very long time, from few hours to more, and requires many resources. So they need to select only subset of tests that can be used for testing. Most of the time, this list is static list that is declared in the first stages of the project. And it's not dedicated for a specific change, but to all changes together. And no matter which change they will do, if it will be in the area of power management or insert a new feature in the area of input-output interface or fix some bug in another area, they will always use the same list, the same static list, which, as I said, is not dedicated for any changes. It's general purpose and was selected in the first stages of the project. And this same test is the first testing in the process. After they check the test by the static list, the test is pushed to the main repository. All the changes of the week and sometimes more are pushed to the same place, and then pass another testing process. This is a full integration test. So in the first step, there was only a few hundreds, and the integration test include much more. But sometimes there is code that pass all the code of the same week pass the static list, but then in the integration test, which ran once a week, even sometimes more, found new bugs, found new failures. And there is few reasons for this. Maybe there is contradiction between the list of between the changes, and it's good that the integration test caught it and we found new bugs. But sometimes, after the hardware developers debug those failures, they understand that the code which was inserted to the main repository included bug. And the static list didn't check all the relevant cases, all the relevant scenarios, and the bug was pushed to the main repository. Experts estimate the time effort of of debugging those bugs in the second stage as 100 times higher, because when someone debugs the failure after you change something, it's easier to understand the cause to the failure, because we know it's related to its change. But when someone starts to debug the failure in the integration test, the failure may be caused by several merge of code, several parts of code, and the debug process is much more difficult and takes much more. So the effort is much bigger, and we want to focus on the left side. We want to improve the static subset of list, and by this, improve all the process. So we know we have a problem because our developers spend a lot of time in debugging, and we wanted to give them a better solution for this problem. So our idea was to create personalized subset of integration test. Instead of using the same static list, to create something that is dynamic, something that you change and depend on the code change. In this case, if Omer does changes in the area of power management, I can understand which are the relevant tests, which are the tests that are likely to fail, to spot failures in the code, and to include them in my list, and remove irrelevant tests. By removing irrelevant tests, I'm saving a lot of time for Intel, because the testing process is very expensive. And by the free budget, I can add new tests, new relevant tests, new relevant that will find new bugs, may find new bugs in the code. So we started to think which data can be used for this solution. And the first thing that we can use is a version control system. For example, Git. We have data about the changes. We know which file were changed, what was the change, who changed it, and when. This is very relevant information. We also have information about the test. We know which test ran, what was the input and what was the runtime, and we can use it also. Another thing is information about the result of the test. I know if the test pass or fail, and I know which failure, because like every developer, we want a variety of failures. We want different types of failures, because different types may learn us about different types of failures that we want, different bugs that we will want to debug. So we have the data set, and we have the problem, and we need to think about a relevant algorithm. And we thought to use an algorithm based on multi-arm bandit. So let's have a quick reminder about multi-arm bandit. The name comes from one-armed machines in the casino. In the casino, each machine has a different probability to win. And the action that we need to choose is to select a machine, which arm to pull. The reward is a payout. We want to gain as much as possible, and to maximize all the rewards that we can gain from those machines. So let's describe that I'm playing with no declared policy, and pull the first arm, and then I continue playing with no policy and just random selection. After a few rounds, let's describe that this is the case. So I pulled only the first three machines, and this is the reward, the payout that I got from each machine. And now I need to decide what to do next, and I want to find a better policy. What should I do? This problem is an example of the trade-off between exploration to exploitation. We want to explore the fourth machine or other unused machines, but we also want to pull the second machine, which has the the best score till now. So I need to understand what arm to choose. And the solution is to use this formula. We can calculate a score, an index for each machine, and then choose the arm with the maximal index. This formula is a combination between my a priori knowledge about the machine, the average reward till now, and the second part is the upper confidence bound, which give me a higher index to machines that haven't checked enough before. So if TK is very small, I will probably choose this machine and not another machine. So let's go back to the example. I can, in this situation, I can use this formula, calculate the index for each machine, and then select the highest machine, in this case, the fourth machine. So we prefer to continue the exploration before selecting the second machine, we gave us the highest reward till now. So this was about the casino, but in our case, Omer, the developer, is interested in getting the best list of tests. So his action is to select a batch of tests, and the reward is a failure. We want to find tests that will fail when we will run them. The goal is to maximize the fail rate. So what is our implementation of this algorithm? It's a small change. It's a potential multi-arm bandit, because we use the files that were changed as features to the model. In this case, if Omer did some change for the feature in the power management, we can collect data from Git and understand which file were changed. In this case, 2 files. For each file, we can create a table which holds the relation between test to file. For each test, we can calculate this index and understand what is the score for this test. So in this case, for the 2 files, we can select the highest test, the test with the highest score, and to put them in our list. Our recommendation is to run those 2 lists and not the static list. So now we have a solution, but we need to train the model, need to prepare this table. For doing so, we had a training process in which we include a big budget for exploration. So every time that a developer did a change, we gave him a list, our best list, and then got the result. And we can calculate this table over and over, and then improve the score for each test. The exploration includes a big budget for exploration. We use the upper confidence bound, but the exploration wasn't enough. And we used another constant epsilon, another budget that is only for exploration, not using the upper confidence bound. After a few weeks, we had data about the relation between test and file, and now we can move to the evaluation process. In this process, we can supply the best list, the best subset of list, to every change. This is a list that's created for each change, dedicated for each change, and the goal is to give the best test, the test that will probably fail on this change. And we continue to do exploration with a very small budget. This solution wasn't so simple. We encountered many challenges during our development. I will share a few of them. The first one is related to exploration. Our environment is very dynamic. Many things can change during the project. For example, the space of the test. During the project, the developers, the hardware developers, can add new tests to the pool of optional tests, and we want to explore them also. Another thing can change is the distribution of failure. Unlike the machines, the casino, which every machine has a different probability, in our case, some tests can fail in the initial stages of the project and later be more stable. So we need to track those changes also. Another thing that can change is the space of files. Files of the project can be changed. The developers can change the directories, they can change the file, they can do many changes, and we should, like before, explore those changes. Another thing that may change is the combination of files that have been changed together. Omer can change one file, two files, three files, or more. It is an unlimited combination, and we want to check all the things together. So our solution for all those things, all the problem, because of our dynamic environment, is to always use exploration. We cannot think that our training was enough. We should continue with our training process through all the projects, because we need to try new things, and we need to continue the exploration. Another problem is the curse of dimensionality. In the casino, in the example, there are only 4 machines, but in real life, there are much more optional machines. Much more, because in our case, there are thousands of possible tests, and we want to explore them all. The exploration process, if we want to explore so much possible tests, it will be very long process. And during all this process, we cannot give any value to our customer. So the solution was to use test clustering. As pre-processing for our multi-arm bandit, we use clustering of the test and split all the tests to groups. Now, instead of thousands of possible tests, we have only a few hundreds. And when we need to explore, the exploration process will be much faster, and the question will converge much faster, and we can give value. We use hierarchical clustering, and we use several measurements for calculating the distance based on coverage and the input parameters. And we use smart selection of the cluster of the test that represents a cluster. So after we finished all this development and encountered those problems, we wanted to evaluate our model. For doing so, we did a controlled experiment in which every code change of any developer passed 2 lists: the static list, the static subset, and our personalized list. And after a few weeks, the results were amazing, because we found out 5 times more bugs, 5 times more different types of failures, and 10 times more test failures, more failures. So because of those results, the decision was to implement this solution in several validation groups in Intel in order to replace the static list by this personalized list. So now Omer and his friend can be more relaxed, because they know their code may continue less failures. They are not introduced new bugs to the main repository. And I hope that I convinced you that personalized testing is possible and efficient. Thank you.